So we just finished talking about basic forces, Newton's three laws, and friction. Those are things that are going to occur throughout all these topics. But now what we're going to do is slightly switch gears and talk about a very specific types of forces. This topic I usually call the special forces. Each one that we're going to talk about is completely unique and doesn't really combine with any other forces that we'll end up talking about. So each one of these can be kind of separated and not really mix and match, unlike before where you can easily have a Newton's first law question mixed with the Newton's third law, mixed with the second, mixed with friction. Here, they're all kind of going to be compartmentalized. So the first one that we're going to talk about are inclined planes. Now, inclined planes, as the name implies, is just a ramp. It's a surface that's raised to an angle. That's pretty much it. But because of this, it's going to end up requiring very special attention. So, for example, let's look at the forces acting on an object that's on one of these inclined planes. So here's my object. We have our force of gravity pulling down, and then the normal force is going to go up at an angle. Remember, the normal force doesn't go up. It always goes perpendicular to the surface and away. Because my surface is now at an angle, it's going to be going up at an angle, like this. It's going to push it away at a 90-degree angle. Now, because these are no longer in opposite directions, we're going to end up having to break them up into their components. Remember, anytime we have a force at an angle, we have to break it up into a x component or a y component. Now, in order to actually think about which one we're going to break up, we're going to actually want to look to see how it moves. Because the thing is, normally what we would do is take the normal force, since this one's at an angle, and break it up into a y component and an x component. But this wouldn't really be the thing for us. Uh, if we just looked at this object and we thought to ourselves, what direction does it move? We know that the object's going to end up moving. Yeah, I forgot to play it, but it's going to end up moving up and down, parallel to the surface. So because it's going to go parallel to the surface, instead of breaking up Fn, which is acting perpendicular to the surface, we're actually going to break up Fg, since that's going to be at an angle to our surface. So Fg is going to be broken up into two forces, a force called the parallel force, which is what's going to pull it parallel to the surface, and the perpendicular force, which pulls it perpendicular to the surface. So what we end up having is this. Fg is being broken up into a perpendicular force and a parallel force. Remember how every time we did a force that was pulled off at an angle, we would immediately break it up into its components and then use those numbers? That's the same thing that's going to apply here. We're going to take Fg, we're going to break it into its perpendicular and parallel force, and then we're going to ignore Fg and only deal with those two numbers instead, because they're what's going to be working with us. Now, to figure out how we're going to break up the parallel and perpendicular, we're going to use a little bit of geometry. Now, you don't have to do this all the time. Once I go through this the first time, I'll give you a little mnemonic device that kind of helps you remember it, and you won't have to do it. But I just want to show how it comes about. So if we look at this angle is 30 degrees. Because this shape here is a triangle, we know that the angles all have to add up to 180. This is 90. These two are going to add up to 90. So if this is 30, then this is going to be 60. And then because we know F perpendicular is by definition perpendicular to the surface, we know that if this angle is 60 degrees, this angle has to add up to 90, so this should be 30. So whatever this angle is, this is the same angle. So if this is at 30 degrees, this is at 30. This is at 40, this is 40. From here, we can use SOHCAHTOA to figure out the parallel and the perpendicular. So this is my angle. This is opposite the angle. So what we're going to do is say F parallel is using sine. So sine theta is parallel over hypotenuse, which is FG. And we get F parallel equals FG sine theta. If we want to look at the perpendicular, we would use cosine since it's adjacent to the angle. So we end up having cosine theta is F perpendicular over FG, or F perpendicular equals FG cosine theta. So our two equations are this: F parallel equals FG sine theta, and F perpendicular is FG cosine theta. So a few things to note. First, these two equations are not on the reference table. This is one of a few equations that you have to memorize. Now, luckily, inclined planes don't appear too much on the regions, especially when dealing with forces, but you do want to be careful, so you do want to remember these equations. Like I said, I'll give you a little memory way to remember it. But some other things that you can use is first, they're both components of weight, so they're both going to have an FG component. So it's going to be an FG in F parallel and an FG in the perpendicular. Another thing that you can think of is that when the inclined plane is flat, horizontal, where the angle is 0, your your perpendicular component should be at its maximum value. So that kind of makes sense. Cosine, when theta is 0, becomes a 1. So this becomes a max and this becomes 0. So you can kind of remember it that way. But the way that I always tell people is that for the F parallel is what's going to cause it to slide down the ramp. The force that slides is the force that sines. So slide and sine and slide. That can kind of help remind you that the force that causes the block to slide down the ramp is the one that has sine. Unfortunately, there really is no good way for the perpendicular one. The best one that I can come up with is that the force that crushes the force that causes. Again, they can't all be winners, but basically the perpendicular force is what's actually pulling it into the ramp. So if this number becomes too big, it will actually crush the ramp and go into the ramp. So parallel causes it to pull down the ramp, perpendicular pulls it into the ramp. Now if we look at this, we can find a few more things. Like for example, if we look at this FBD, what should the normal force be equal to? Typically, when we had the object on a flat surface, the normal force was always equal to Fg. However, I did try to reiterate multiple times that it wasn't always equal to Fg. Here, if we look at this, we can see that Fn actually ends up being equal to F perpendicular because of the fact that they're in opposite directions. This is one of the reasons why I explicitly always reiterated that Fn equals whatever's opposite it. And then also in this FBD, the normal and perpendicular cancel each other out. In this specific case, F parallel is being unbalanced. So you'd use F parallel in the F net equation to figure out what the acceleration is. But for the most part, when you're using F net equals ma, you're most likely going to be using the parallel force and any other force that's acting along the incline. If there's friction, you would also include that in there, or any applied forces. All right, so we'll work on using those equations. So pause the video, work itself, and we'll go over in a second. All right, so once again, the main thing with these inclined planes is you have to kind of rephrase whatever they're asking to figure out whether they're looking at the parallel force or the perpendicular. So again, the acceleration that's pulling it down the ramp. This is being caused by the parallel force. There's no friction, so the only force that's acting horizontally, or I shouldn't say horizontally, parallel to the surface is this F parallel. So when they ask what's the net force, they're really asking for what's the parallel force. So F parallel is Fg sine theta. The force that slides is the force that sines, sine and slide. They tell us that the weight is 8 newtons. Because this is already in newtons, I just leave it like that. And we know that the angle is 15 degrees. So 8 times sine of 15 gives me 2.1 newtons. All right. And that's pretty much it. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so they want us to find the FBD, the forces that act on this block. So first off, just to clarify, here they're using FW instead of FG. If you remember, FG always acts straight down. When we actually do some math, we have to break that up into its components. But for now, we're just going to leave it as its normal vector going straight down. We know that the normal force is going to end up going up at an angle perpendicular to the surface. So far, the only FPD that looks like that is this one. So Fn going up at an angle, Fg going straight down, and friction would end up acting parallel to the surface. Again, because all the forces that act on this are going to be either going parallel to the surface or perpendicular, that's the reason why we're going to be breaking Fg into the perpendicular and parallel components. Here's the next question. Pause the video work itself and we'll go over in a second. All right, so here, do a quick FBD. So again, instead of doing FG going straight down, I'm going to do an F perpendicular inward. There's going to be an F parallel going along here. There's going to be an Fn going up at an angle. Because it's smooth, that means there's no friction, and it doesn't seem like there's going to be an applied force. So these are the only forces acting on it. Now, the perpendicular force is going to be Fg cosine theta. So Fg is going to be, well, this is the mass. So the weight, Fg is going to be 30 times 9.8, which is going to be about 300 newtons. Remember, Fg always has to be in newtons. And then my angle is going to be 30 degrees. So F perpendicular is going to be 300 times cosine of 30, which is about 260 newtons. And then the parallel force is going to be Fg sine theta. So it's going to be 300 times sine of 30. Plugging this in, we get that the parallel force is 150. So again, what this is saying is that of the 300 newtons of the weight of this object, 260 newtons is pulling it into the ramp and 150 newtons is pulling it down the ramp. Remember, these two numbers don't have to add up to 300 because they're, vectors, and that's the way it works. So F parallel is going to be 150. This is going to be 260. Now here, they want to determine the normal force. So again, the normal force is going up at an angle. The force directly opposite it is the perpendicular. So this is going to be 260. And then for here, determine the acceleration. I'm going to use F net equals ma. My net force is 150. And my mass is 30 kilograms. Plugging that all in and solving for acceleration, I end up getting that acceleration should be 5 meters per second squared. All right, and that's pretty much it. So here's the next one. Pause video, work itself. We'll go over in a second. All right, so once again, I have F parallel, F perpendicular here and F parallel over here, and Fn going up. Once again, no friction, no applied force because smooth and there's no person. Once again, the perpendicular force is Fg cosine. So Fg is going to be 10 times another 10, so 100 newtons times cosine of 60, which means that my perpendicular force is going to be equal to 50 newtons. Here, F parallel is Fg sine theta. So 100 sine of 60. So 100 times sine of 60 is going to be about 87. Going to part C, the normal force. Directly opposite it is the perpendicular. So this will end up being 50 newtons. And this will be the same thing. I use F net equals ma. 87 equals 10a. My acceleration is going to be 8.7 meters per second squared. All right. Here's the next question. Pause video work itself, and we'll go over in a second. All right. Now for this one is a lot trickier. What we want to do is look at this diagram. They don't give us the full FBD, so we want to actually finish it up. So there's a parallel force going down and a perpendicular force going in and a normal force going up. Remember, you can have more than one force going in the same direction. So I have 3 newtons pulling it down, I have the parallel force pulling it down, and this force pulling it up. They want to know what this force is. Because of the fact that it says the ramp travels at a constant velocity, I know that whatever force is pulling it up has to be equal to the total force pulling it down. So we know there's 3 newtons of force pulling it down. Let's figure out what this parallel force is. F parallel is Fg sine theta. Once again, they tell us that the weight is 10 newtons. I'm not going to do anything with that because it's already in newtons. And this is sine 30. So this will end up being 5 newtons. So I have 5 newtons caused by some of the weight pulling it down, and I also have friction of 3 newtons pulling it down. In total, I have a total force of 8 newtons pulling down. Therefore, the force pulling up has to also be 8 newtons. This has popped up on the Regents as a multiple choice question. It definitely is one of the trickier things, but if you remember the statement I said about how a lot of these questions are like magic tricks, if they're looking for the force pulling up, you have to look at the forces pulling down. So not only is the 3 Newton force pulling down, but the 5 newtons is also pulling down. Another way that you can kind of remember or note from this diagram is that even though these vectors aren't drawn to scale, the fact that they made this arrow longer implies that it has to be more than 3 newtons. Even though we haven't been doing that, the diagrams that the Regents give you, they do try to convey that information that if an arrow is longer, it is bigger. So you can use that to also gauge whether or not the number should be bigger or smaller or equal to whatever forces they tell you. All right, here's the last question. So pause the video work itself and we'll go over in a second. All right, so once again, we're going to do a quick FBD. So we have a perpendicular force pulling in, a parallel force pulling them down. We have a frictional force pulling up to keep them at rest. And then we have the normal force pulling them upwards. So again, because of the object is at rest, here it is, at rest, we know that friction and the parallel force have to be equal. So when they ask what's the frictional force, I know that that's equal to the parallel force, which is Fg sine theta. Fg is going to be 8,000 newtons. I just take the 800 kilograms times it by 10, and then my angle is 45 degrees. If I plug that in, 8,000 times sine of 45, I end up getting, I'm going to round it, 5,700 newtons. Here they want to know the coefficient of friction, so that means I'm using FF equals mu Fn. I already have what FF is, so I actually need to figure out what Fn is. Again, Fn is going up. It's being balanced by the perpendicular. Now the perpendicular is going to be Fg cosine theta, but one thing to note is the Fg is the same as here. It's going to be 8,000. Sine of 45 and cosine of 45 are the exact same values. So I actually know that the normal force and the perpendicular force are also equal to 5,700. So my equation ends up being 5,700 newtons for the frictional force equals mu times 5,700 newtons for the normal force. Divide that over, and I get my coefficient has to be at least equal to 1. And that's basically it. So the big thing with the inclined planes is to make sure that you first take your weight and break it up into components. You are no longer drawing in FG going down. Instead, you're going to be drawing F parallel going down the ramp and F perpendicular going into the ramp. Another thing that you need to note is that Fn is not going to be equal to Fg anymore. It's going to be equal to F perpendicular because those are the two forces that are acting opposite each other. Though I don't see it happening, you could also have an applied force that goes perpendicular to the plane as well. So you would deal with that. But for the most part, Fn is going to now be equal to F perpendicular. And then when you do anything dealing with the acceleration or the net force or anything like that, F parallel and and any other forces going parallel to the surface, those are the forces that you're looking at. Again, what you're doing is you're taking this entire diagram and rotating it so that it now becomes a flat surface. And if you actually tilt your head to the side and just visualize this as being on a flat surface, you'll see that this looks like one of our normal FBDs that looks like this, with down, up, left, and right. So that's why we're going to be changing the FG force. If you have any questions, please let me know. Message me on Remind, join to Extra Help, or you can ask me questions in class. Otherwise, I'll see you later. Good luck and have a great day.